Suppose f is a function from a to b, and r is a relation on a. We're going to define a new relation s on the set B in the following way. Okay, so in order to understand what s is, let's go ahead and draw a picture of a set A and a set B, a function f from a to b, and we start out with some relation r on the set A, and we're going to define a relation s on the set B as follows. An ordered pair x, y is going to be in S. Okay, so let's consider an x and a y over here in B. It's going to be in there if there exists a u and a v over here in A, u and v, such that these three things are true. F of u equals x, f of v equals y, and finally u and v are related by r. Okay. So, oops, that arrow should go the other way, right? U is related to v. And if that's the case, then we get that x is going to be related to y by s. That's the definition of x, y being in S. Okay, so that's what S is. Now, part A of the problem says we're supposed to prove that if the original relation R is reflexive and the function f is onto, then the new relation S is also reflexive. Now, as I was going about proving that, I realized that actually a stronger statement is true. If we go ahead and suppose that R is reflexive, then it's not just true that if f is onto, then S is reflexive. The converse of that is also true. If S is reflexive, then f has to be onto. Okay, so let's prove both of those directions. So I'll prove this second statement here, which is a strengthening of the first one. Okay, so let's begin by drawing a picture of that. I'll clear it up a little bit here. Okay, so we're supposing R is reflexive, and also supposing f is onto, and we want to show S is reflexive. So to show S is reflexive, we should let B be an arbitrary element of B. We want to show that B is related to itself by S, right? So you can follow along in the proof over here. Suppose f is onto, let B be an arbitrary element of B. We're going to show that BSB. Okay? And, well, we can go ahead and use that f is onto to arrive at some element A back here. I think I called it A naught in the proof, so I'll call that A naught, such that f of A naught is equal to B. That's because f is onto. And then we also are assuming that R is reflexive, and so anything back here in A is going to be related to itself by R. All right. Well, and then if we put that together, we have, we're trying to figure out that BB is in S, right? And so, okay, well, we have A naught, which is an R, and f of the first A naught is the first B, and f of the second A naught is the second B. And so this exactly matches the what we need to know for BB to be in S, okay, according to the definition. So there we have it. If that last step was a little confusing, then go ahead and watch the part of the video where I go through the givens and goals table, and hopefully that'll be clear at that point. Okay, so that proves the forwards direction of my if and only if statement. Now let's try the backwards direction. So this time we're going to suppose S is reflexive and show that the function is onto. Okay. So if our goal is to show the function is onto, we're again going to let B be an arbitrary element of B, and we have to find something back here in A which maps to it, right? Well, we know that S is reflexive, so we know that B is related to itself by S. And so, well, if BB is in S, then we know that this statement's true, right? There exists a U and a V back here in A such that, well, this is BB, right? So f of u is B and f of v has to be B. So these guys both map to B under f. And, okay, we also know that u and v must be related by R. But we don't even need that, right? We're already done. We're just trying to prove that. I'm losing my drawings here. We just had to prove that I'm trying to show f is onto, so we just had to find some element back here. I guess in the proof I called these u naught and v naught, which map to b. And in fact, we have two of them, right? We have more than we need. So we've certainly shown that f is onto. Okay, so that takes care of part A. But let's go ahead and I'll go ahead and go through the givens and goals tables. If you already feel like you understand the proof and you could have reconstructed it based on just the picture here, then that's fine. You can go ahead and fast forward to part B a little bit further down the video. Okay, so here's what we're trying to prove. Suppose R is reflexive, and then we're going to show this if and only if statement, and we'll do the forward direction first. And we'll do it by direct proof. So suppose f from A to B is onto. And then we just want to write down the definitions of what it means for these relations to be reflexive, and the definition of f from A to B being onto. Okay. Now we've got a bunch of universal statements, and we will prove the universal by letting B be an arbitrary element of B. And okay, well, eventually we're going to be using the definition of S, which talks about ordered pairs, and so I'm just going to write this in the other manner, that the ordered pair BB is in the relation S. Okay, and then looks like we have a universal instantiation over on our given side, where B is just itself B, so we got that statement. And okay, let's go ahead and write out what this means using the definition of S, right? So x and y are both B, and then we just write out this whole statement, replacing x and y by B. And we get this. That's our new goal. Existential instantiation gives us an A naught in A such that f of A naught equals B. That just came from f being onto, so we found something which maps to B. We're following the exact same argument here as we did in the picture earlier. Okay. Now we got to prove the existential here, and so, well, what ends up working is that u and v should both be this A naught that we found over here, right? So that's my guess, that u and v are both A naught, and so I have to show that A naught is in A, which I happen to already know, and I also have to show that this statement is true where I replace the u and the v by A naught. Okay, so I have to show that f of A naught is B, f of A naught is B, that's the same thing, and that A naught is in R. And so I'm basically there. Let's just tidy it up here. Universal instantiation gives us that, yes, this element in A is related to itself by R. And okay, there was our first goal. And those two together give us our second goal. Okay, so that finishes this first direction of the proof. And now for the backwards direction, we're going to suppose that S is reflexive and show the functions onto. That's the converse of what we just did. So direct proof again, definition again, definition of S being reflexive, and you notice I didn't bring the R being reflexive down. I don't think we need that for this direction. Okay, so proving the universal, we'll let B be arbitrary, and we can do a universal instantiation there to find out that this arbitrary B is related to itself by S, since S is reflexive. Okay, and that means BB is an S, and so once again we write the definition of that out using what's given. And existential instantiation gives us a U naught and V naught, each of which map to B, and they happen to be related to each other, but remember, we don't care about the related to each other part, because we're just trying to find an element of A which maps to B, and we've done it, right? U naught is in A, and f of U naught equals B. So finishes that off. And brings us to part B of the problem, which is similar, but it's, instead of being about the relations being reflexive, it's about transitivity, and instead of onto, it's about one-to-one. Okay, so if R is transitive and F is one-to-one, then S is transitive. Well, let's try and understand why this might be true. So here is my set A again. Here's my set B, and function F, relation R, and then relation S, which is defined in terms of R and F as above. Okay, so R is transitive, F is one-to-one. We got to show that S is transitive. So how do we do that? Remember, we suppose we have maybe I'll start at the top here. Suppose we have an x, y, and z in the set B, and suppose that xy is in S and yz is in S, and then we want to know whether, well, if we're going to show it's transitive, we got to show that xz is in S, right? Okay, good enough. Now, the fact that xy is in S means that we have this, right? We have a u and a v, so u and a v such that u maps to x under f and v maps to y. So these arrows are all f arrows. And moreover, u v is in R. Okay. And then we also have that y is related to z, that yz is in S. And so we again have a couple elements in A which map to the right things and which are related by R. But there's no reason to suspect they have to be the same as either of these, right? So let me, for reasons that you'll see in a moment, call the first one v prime. That would actually be the u up here. And the second one I'll call w. And so v prime is the one that maps to y, w maps to z, and then if yz is in S, then we know that v prime w is in R. Okay, that's an R. All right, good. So, all right, now we want to use the transitivity of R, but it's not immediately clear that we can use that here, right? Okay, but the other thing we can use is that f is 1 to 1. That's really the key here, because look, we have v and v prime both mapping to y under f, and we know that if f is 1 to 1, that means that v and v prime are actually equal. Okay, so now all of a sudden we have that uv is in R, and instead of v prime w, I can think of this as vw is in R, and putting those together with the transitivity of R does give us that w is in R. Okay. Oh goodness, my computer doesn't like all these things I'm drawing now. Okay, let me make a little bit better R there. Okay, and if uw is in R and u maps to x and w maps to z, then by definition of S, that implies that xz is in S. So S is transitive. All right. Now that's what you see in my proof over here. And again, if you you might want to try to sort of pause it and write this up by yourself and compare, or at least read through what I have here. And if you understand that, you might as well stop now. But if you want some more detail, go ahead and go through my givens and goals table with me here. Okay, so R is transitive and f is 1 to 1. Show that S is transitive. Definition of transitivity. And we will prove the universal by letting x, y, and z be arbitrary elements of B. And you remember all this from our picture, right? And then we'll do direct proof. Suppose that x is related to y, y is related to z. Prove that x is related to z. That's what it means for x, z to be in S. And that's what it means for x, y to be in S and y, z to be in S. Okay. Now, a whole bunch of existential instantiation gives us our u naught and v naught and our v naught prime and w naught, just as we had in the picture, with the corresponding facts about those variables. And definition of R being transitive and definition of f being 1 to 1. Okay, so we've got all the ingredients and need some more space, so let me just take that last bit and move it up to the top here. From all this, we can conclude that well, look, we're just saying that v naught maps to y and v naught prime also maps to y, and so they're both equal to y. They're certainly equal to each other. And okay, we also have from these same two statements that what's left, that u naught maps to x and w naught maps to z. Okay, and these guys are related. We're going to need all that. Now, by universal instantiation applied to v naught and v naught prime, we get that conditional, which we can then combine with modus ponens, combine with this to, and remember this is just the fact that f is 1 to 1, right? So we're saying that because the images are the same, the outputs are the same, the inputs must have been the same too. Okay. And now if those are the same, then here I had the v naught and v naught prime. I can just replace the v naught prime by v naught, and I can also rearrange these in a slightly different order. And universal instantiation on this definition of R being transitive. Okay, and that transitivity together with what I know, these two pairs that are related by R, gives me that U naught's related to W naught. And that's just what I need because U naught maps to X and W naught maps to Z. And so by definition of, what it means for, what were we trying to show? That I guess XZ was in S, right? And this was the definition of that. So we have U mapping to X, W mapping to Z, and U and W are related back in R. Therefore, X and Z are related in S. Okay, and so that's the same thing we wrote up over here. Now, before we stop, you might be wondering, you remember for part A I said that the converse was also true, that under the assumption that R is reflexive, if S is also reflexive, then F must be onto. You might wonder whether the same is true in B, right? If we assume that R is transitive, and we assume that S is transitive, does it necessarily follow that F is 1-to-1? So I want you to pause the video and see if you can figure that out for a moment, and before I give you the answer. And it seems like that's not true, actually, because you can take a silly function. You have some set A, and maybe the set B is just a single element, right? So you're having, F just takes everything in A and maps it to this single element of the set B. You can draw it as a set if you want with one element. And well, any relation S on B is going to be transitive, right? So I mean, either it's the sort of empty relation or it's the relation that just has this element related to itself. And you could certainly start with the transitive relation R here on A, but the function is very much not 1-to-1. Right? It's everything to 1, and so that would be a counterexample to sort of the converse in part B here. All right, we're done.